Greetings. In this chapter, we'll be talking about a number of topics you've probably had before, but these topics will be a foundation for all of our future discussions. We'll begin with the notion of real numbers. Now, recall that real numbers are often illustrated using a real number line. And on the real number line, positive values lie to the right of 0, negative values to the left. 0 is referred to as the origin of this little coordinate system for the real number line. Now, when we take a number such as, let's say 2.3, and let's say that we want to construct the graph of this. Well, the 2.3 is called the coordinate of a particular point that we're going to find on the number line. And that once we find that position on the number line corresponding with that number, we are constructing a graph. So the dot is a graph and the number is the coordinate corresponding with that position. Now, the interesting thing about the real number line and real numbers and points on the number line is this, that there is a correspondence between those two ideas. That is, for every real number, there is a position on the real number line corresponding with it, and for every point on the real number line, there is a real number to describe its position. So that establishes then a one-to-one correspondence between real numbers and points on the number line. Now, you may remember that real numbers are actually composed of a couple of very significant sets of numbers. Rational numbers are defined as all the numbers in the world that can be written in the form a over b, where b is not equal to 0. Now, this would be common, ordinary, everyday household fractions like 2/3, but also a number like 5 can be written in this form because 5 can be written as 5 over 1, so it's a rational number. 35 hundredths can be written as 35 over 100. You see, the fractional form of the decimal number gives us this form and therefore a rational number. 4 1/2 can become an improper fraction in the form a over b, therefore, and so a rational number. And then you might be thinking, well, gee, what numbers would not be rational? What numbers would not fall into this rather enormous set of numbers? Well, irrational numbers are not part of this set, and those numbers are never-ending and never-repeating decimals. And some popular irrational numbers are the square roots of non-squares, like the square root of 5, and the naturally occurring constant pi and the naturally occurring constant e are members of this set. Well, when you take the rational numbers and the irrational numbers and you put them together, you have the set of real numbers. That's what these numbers are all about, and that's the number system that we'll be talking about, at least at first in this course. Here's a real number line. Now, you may recall that using the number line, we can establish an order relationship between any two numbers. For example, if we're thinking about the number 1 and the number 4, we say that 1 is less than 4. And 1 is less than 4 because, well, here's 1, here's 4. 1 lies to the left of 4 on the number line, and therefore 1 is less than 4. Numbers that lie to the left are less than numbers that lie to the right. Numbers that lie to the right are greater than numbers that lie to their left. 3 is greater than -5 because 3 lies to the right of -5 on the number line. It's just a position idea. -4 is less than -1. Here's -4, here's -1. -4 is to the left, and therefore -4 is less than -1. -2 and -5. Now, this is if there's any challenging situation involved with this order relationship idea, it is a situation in which both of the numbers are negative. And it's important to actually think about their position on the number line. Here's -5, here's -2, and the comparison of -2 to -5 is that -2 is greater than -5 because -2 lies to the right of -5 on the number line. So -2 is greater than -5. Now, here's an interesting description of a variable x. Now, a and b are some constants, let's say, that are real numbers. And we can say here that x is between a and b. Actually, we would read this from left to right. A is less than x, and x is less than b. So x is between a and b. Now, in this kind of description, we can use an interval notation to describe this situation. And the interval notation would be this. It would be that the x values that we're talking about, which are between a and b, are in the interval from a to b. And this parenthesis notation here indicates that the a is not a member of this group of x's that we're talking about, nor is b because of this parenthesis notation. Recall that if we want to include an endpoint of an interval, we use the bracket notation. For example, here, this is read, a is less than or equal to x, and x is less than or equal to b. And the interval notation is a to b like this with a comma, and then the bracket notation to indicate that the a and the b are included in the interval. Now, when both ends are not included like this, it's an open interval. When both ends are included in the interval, it's called a closed interval. Here's a situation involving a graph. Now, we should be able to work among these three different forms that we're looking at. We're looking at a graphical form, we're looking at an inequality form, and we want to look at interval notation as well. So those three ideas should be interchangeable pretty much in describing groups of numbers. All right, here we have a shaded region between 2 and 7, and we're including the 7, but we're including the 2, but we're not including the 7, and we know we're not including the 7 because of this parenthesis notation, and we're including the 2, and we know that because of the bracket notation on this end. Now, the inequality describing the situation is this. 2 is less than or equal to these x values that are illustrated with the shaded region, and x is less than 7. Now, this is the interval. X is between 2 and 7, but x can take on the value 2, but cannot take on the value 7. And in interval notation, we say it's the interval from 2 to 7, including the 2, but not including the 7. So that's the idea. Now, here we have a shaded region that is between -3 and 5. And with inequality notation, it would be -3 is less than, strictly less than because of the parenthesis idea here. So -3 is less than x, and x is less than or equal to 5. In interval notation, it's the interval from -3 to 5. Strict notation here, and therefore the -3 is not included, so we use parenthesis. And over here, x is less than or equal to 5. 5 is included, so we use the bracket notation. Here we have a shaded region that is to the left of 4 on the number line, and we say then that x is less than 4. Now, it's strictly less than 4 because of the parenthesis notation. The interval notation is rather interesting because we're going from -infinity, you see, from -infinity all the way to 4. So it's from -infinity to 4, and we never put a closed indicator on an infinity symbol. So we leave this open on this end, and this is open as well because the 4 is not included from up here. On this one, we're talking about values that are to the right of -3 on the number line, so we're talking about x values or any letter. I could use a different letter than x. I'll use n here is greater than or equal to -3. And that's the inequality. The interval notation would be the interval from -3 to infinity. So -3 to infinity, including the -3, but not including infinity. Sometimes the inequality describing an interval on the number line is a little bit disguised. Here's such an example. Another way to look at it is this. We have an inequality here, and we'd like to solve it. Now, the idea of solution is very important to us, and it is quite consistent whether we're talking about solving inequalities or solving equations of all different kinds. And it's a notion that we're looking for, when we're looking for a solution, we're looking for a value or values of a variable or variables that will make the statement of inequality or the statement of equality true. So here we're looking for values of x that will cause this statement of inequality to be true. Now, to find such values, we actually go through a process of isolating x on one side of the inequality or the other. And it's much the same as the process of solving linear equations. This is a linear inequality. Now, to do that, we'll isolate by first clearing the constant -4. We add 4 on both sides to find 3x is less than 5 plus 4. So 3x is less than 9. We can divide now on both sides by the coefficient of x. So here's what we're doing. And we find that x is less than 3. Now, this is implying that for all values which are less than 3, this original statement of inequality is going to be true. Now, we can test a few points. We can say, well, let's see, 0 is less than 3. Would 0 make this true? Well, let's see. If x is replaced with 0, then this term goes out and we have -4 is less than 5. That's a true statement. So we know that 0 is part of the solution set. Now, we don't know exactly the complete solution set just by testing one point, but it sure gives credence to the idea that we probably have a correct answer here. Besides, this is a pretty easy problem. But x less than 3, we can use interval notation now to indicate the interval in which our solution points occur. And we could do that just by saying, well, gee, these are the values from -infinity to 3, not including the 3, and we never include the infinity symbol in this notation. All right, here's one where we have x on both sides of the inequality symbol, and we go through the same way that we did before. Let's say that we want the values involving, or excuse me, the terms involving x on the left and the terms that are constant on the right. We would subtract 5x on both sides to clear this. We would add 3 on both sides to clear this. So we have x minus 5x. And then on the right, we have the 9 coming down, and then adding 3, we get this. Collecting on the left, we get -4x, and on the right, 9 and 3, 12. Now we need to divide by the coefficient of x in order to isolate that x. But this situation is one of the nuances in solving linear inequalities. And the nuance is this, that when we divide by a negative value, we have to change the sense of the inequality. So here's how it goes. When we show that we're dividing by -4 on both sides, the sense of the inequality changes, and away we go. These go out and we have x is greater than or equal to 12 divided by -4 is -3. So x is greater than or equal to -3. Gee, we can test that. Again, 0 falls in this interval, so we could use 0 as a test point, I suppose, just to kind of verify a little bit that this may be the correct interval for our solution points. But let's see, if we replace x with 0, this term goes out, that term goes out. We have -3 is less than or equal to 9. Certainly that's true. Okay, and we could write the interval notation for it here. Here's another kind of inequality. It's actually a couple of inequalities in one. It's -7 is less than this expression, and this expression is less than or equal to 13. To solve an inequality like this, we want to isolate x in the middle. And to do that, we'll clear the constant first. And let's do that. We'll subtract 5 in all parts, so we have -7 minus 5. When we subtract 5 in the middle, it'll go out. And then on the right, we get this. Now collecting, we have -12. And on the right, 13 minus 5 is 8. Now we need to divide by -2 to isolate the x in the middle. But rather than just divide by -2 on both sides of the inequality, we actually have 3 parts here where we have to divide by -2. We're dividing here, we're dividing here, we're dividing here. A good way to show it once we made the decision to do that is to just say we're taking this and dividing by -2. But let's be careful. We're dividing by a negative. So, gee, maybe we better not take that little shortcut. You see, because since we're dividing by a negative, we need to do this. See, we're dividing by -2, so the sense of the inequality needs to change. So we should write a step that indicates the division of -2 and the change of the sense of the inequality. All right, -12 divided by -2 is 6, is greater than, these go out and we have x, and then on the right, 8 divided by -2 is -4. Now x then is between 6 and -4. So this is the interval from 6 to negative 4. Gee, we usually write interval notation with the smaller number to the left, you see. And so we would write the negative 4 like this, and then the 6. And now x is greater than or equal to the negative 4. So negative 4 is included in this interval. 6 is not included, so this would be the interval notation. Here's one involving fractions. Now recall that when fractions are involved in either equations or inequalities, you want to clear the fractions as the first order of business. And to do that, you identify a common denominator and multiply through by it. The common denominator here is 6, so we'll multiply through by 6. So we're really just taking 6 and multiplying times this term, and then 6 times this term, and then 6 times the 5. Now, notice that in multiplying 6 times this term, I'm just putting 6 as a factor in between this minus sign and the x over 3. I'm just popping it in as an additional factor there. And it's okay to do it that way, and I think it's the easiest way to do it. The 2 and the 6 cancel here, leaving 3. This is 3x then. The 3 and the 3, 1, 3 and the 6, 2. So this is negative 2 times x, negative 2x. And on the right, 6 times 5, 30. Collecting on the left, we find that x is greater than 30. This next one is quadratic in form. We have a second degree x, and the strategy for solution is quite a bit different than the solution strategy for linear inequalities. With quadratics, the idea is to put all the terms on one side and then factor, and then kind of go from there. And I'll show you what we do from that point. But the first idea, the first notion is to put all the terms on one side. I'm going to kick them to the left here. We have x squared, then subtract x and subtract 6 on both sides to get this. And now factor, and we get this. Now once we have a factored form, we identify the zeros of the factors. Now that is, identify the value of x that will cause each of the factors to become 0. Those are called critical numbers, or critical points if you will, or significant points. You can name them any way you want to, but they're important in our study here. I'm going to call them critical numbers. Tell you why they're critical in a minute. So the critical numbers are the zeros of each factor, and those are x equals 3 and x equals negative 2. Now from this point, at this point, we construct a number line and identify, actually I don't need this, generally when you write a number line you can, it's a convention. In some textbooks you write arrowheads on both ends. On some textbooks you emphasize the positive direction by putting an arrowhead only on one end. And generally it's the right side, but it's kind of arbitrary. X is 3, x is negative 2. The relative position of those two would be about like this. And now we have subdivided the number line into 3 regions. You see 3 intervals, the interval out here, interval in between, and the interval out here. And we will test those intervals. We will test to see if a value in the 3 intervals will cause the statement of inequality to become true. Now, if the statement is true for one point in the interval, it turns out that it'll be true for all points in the interval. If it's false for one point, it'll be false for all of them. So if we're going to take a test point that's to the left of negative 2, we might try negative 10. Now, we could go up to the original inequality if we want to, or we can use this equivalent inequality as a test point. And I think I'd like to use this because it's going to be useful in a minute to describe to you why the critical numbers are indeed critical. If we choose as negative 10 as a test point, we have negative 10 minus 3. That's negative 13. I really don't care about the 13 part. I care about the negative part. Because notice that the nature of this inequality is that we have the product of 2 numbers, and that product is less than 0. That product is negative. So it's really the idea of positiveness and negativeness of our 2 factors here that will tell us whether or not this product is going to be positive or negative. So let's see, this is negative. You see, in this region, all of these values are going to be negative. And in this region, let's see, for negative 10, You see, any numbers to the left of negative 2, we have numbers to the left of negative 2 plus 2, that's going to be negative. Negative times negative, positive. Positive less than 0? No! So the numbers in this region do not solve the inequality. They're not part of the solution set. Now, for numbers that are in between these two, let's take a number like, 0 is between these two. So if we use 0 as a test point, 0 minus 3, that's negative. 0 plus 2, that's positive. Negative times positive, that's negative. A negative number less than 0, yeah, that's true. So the numbers in this region will solve the inequality. Now, the critical numbers themselves are critical because they are the places on the number line where the sign of each factor will change. That is, if think about marching along the number line. If we're out here, now think about this factor. If we're out here to the left of negative 2, then this factor is going to be negative, negative, negative for all the values over here. But as soon as we jump to the right of negative 2, a number that is a little bit bigger than negative 2, like, negative 1, you see, something like that, or negative 1.9 or whatever, then plus 2 makes this positive. So this value is critical because it is the spot where a factor changes sign as we're moving along the number line. It's a good way to look at it. And this one changes the sign of, this critical number 3 has a sign change at 3. So when x is above 3, larger than 3, minus 3, it's positive. When x is below 3 minus 3, it's going to be negative. So that's the nature of that critical value. Now let's test the interval to the right of 3, a number that's out to the right of 3, a number greater than 3, and all we need to do, we don't need a specific number in the region, all we need to do is think greater than 3. Well, what does that do to the sign of these two factors? Greater than 3 minus 3, that's positive. Greater than 3 plus 2, that's positive. Positive times positive, positive. Positive less than 0, no. So numbers in this region don't solve the inequality. It's just numbers that are between negative 2 and 3. Now we need to test the critical values themselves. It'll sometimes be the case that the critical numbers themselves will be part of the solution, and other times those numbers will not be part of the solution. If x is negative 2, then we have negative 2 plus 2, that's 0. It'll cause this product then to be 0. 0 is less than 0? No, that's not true. So negative 2 is not part of the solution region, and nor is 3 for the same reason. If we replace x with 3 in this factor, we get 0. The product here is 0. 0 less than 0? No, that's not true, and therefore 3 is not part of the solution region. So the solutions are values that are between negative 2 and 3, and we can say that, remember, in a number of ways. And the interval notation is probably the easiest. It's that we want x values in the interval from negative 2 to 3 and not including the endpoints. Here's a word problem having to do with an inequality. It says the revenue for selling x units of a product R equals, and then 115.95x. And the cost of producing x units is this equation. So we have a revenue equation and a cost equation. To obtain a profit, the revenue must be greater than the cost. For what values of x will this product return a profit? Well, it says something about an inequality, and let's just set up that inequality. It says the revenue needs to be greater than the cost. That makes sense. So we can start with what makes sense. You see, we can say, well, to set this up, we know that revenue needs to be greater than cost. But we have an expression for revenue. We have an expression for cost. And let's just replace those expressions in here and then solve the resulting inequality. And that's what this is all about. So we have, let's see, the revenue expression is 115.95x. And the cost expression is 95x plus 750. Now let's see, to solve, I'll subtract 95x on both sides. And we get, let's see, I think 20.95x is greater than 750. Dividing on both sides by 20.95, this is what we're doing. X is greater than, now we break out the calculator and take 750 divided by 20, divide by 20.95, it's about 35.8. So for units that are greater than 35.8, gee, we generally talk about whole numbers of units when we're talking about production. So it would be 36 that we're talking about. So X needs to be greater than, or it could be equal to, 36 units in order to return a profit.